All right. Good morning, folks. Let's go ahead and get started here, and let's try to finish up with the discussion of mechanisms here. And I just want to make sure you understand then that this idea of mechanisms that a chemical reaction occurs in individual steps, and that we are trying to elucidate those steps. This idea of mechanisms is what we propose is happening based on some of the data that we have collected. Okay? So the idea here of elementary steps, this idea of molecularity, all those ideas are meant to try to explain then how a particular rate law that we come up with, how a particular rate that we determine kind of fits in with the overall chemical process. So when we talk about, and let me go ahead and share and open up and start and share my screen here with you. When we talk about elementary steps, these elementary steps, remember, are simply then individual steps that occur during the course of a chemical reaction to get from the start to the finish. What we learned up until this point is that we learned then that a chemical reaction involves reactants, involves products, and that the amounts of reactants and products have to balance out somehow, and that's what stoichiometry is. And that's what we've learned up until this point. We've learned that the chemical process reaches equilibrium, and that they occur at certain rates, the kinetics of it. And so this idea then that chemical reactions do not occur as written in as written, okay, is something that still, I think, folks new to mechanisms have a hard time wrapping their mind around. But that's why I tried to bring up the analogy of cooking, or bring up the analogy of putting together a piece of furniture. There's always a set of steps that you have to go through in order to get from the start of what you start out with, the material, the ingredients to start out with, and the end product. The same thing holds true then for chemical reactions. Most chemical reactions, many of them do not go, I'm sorry, from start to finish directly. They have to go through these multiple pathways in order to get to the end product, which is the product that we want to look at. Okay? And so because we are aware of that, we try to come up with these mechanisms. And the way that we are able to obtain these mechanisms is to make sure then that that they accord with the empirical data that we have collected. One of which then is the rate law, the rate laws that we come up with for these mechanisms. Okay? And so that's what we want to try to discuss today. The idea of reaction mechanisms is very important, folks. That's why I have to introduce it. We're spending a little bit of time with this. It's very important. You move on, and everything is about mechanisms. What are the steps that go into getting from start to finish? Okay, and so this is going to be your introduction to mechanisms. And so make sure you understand then that this is an important concept. We only spend this one section on it, but it is an absolutely important concept, as especially for you folks who are moving forward with chemistry, because you want to pursue a career in science or medicine. Okay. All right. So with that said, then the individual steps in a mechanism. So if you go from start to finish, the individual steps in a mechanism, we call those the elementary steps, and that's what we have here. Okay. An elementary step itself is a chemical reaction. So you want to think about this. You have the overall chemical reaction. Okay, and then in the individual steps, you have individual chemical reactions that gets you to a new product. That product's used in the next chemical reaction that takes you to a new product, and so on and so forth until you get to the final product. Okay? And so these elementary steps are chemical reactions. And so we can define these chemical reactions, okay? And these are one-step chemical reactions. Okay? And so we can define the kinetics of these elementary steps very simply, okay, by the number of reactants that mix together. Okay? And that's what molecularity is. Molecularity is just a way that we can define the number of reactants that get together to form the product. Okay? So in the elementary steps, okay, so these very simple basic reactions, we actually can use the balanced equation for these elementary steps to determine then the rate. The coefficients do correspond to the exponents in the rate law. And that's what we were talking about yesterday. That's what we were going over through yesterday in this slide right here. And so that if you have a unimolecular reaction, a unimolecular elementary step, it's one reactant. And if you notice to the rate law, then if you look at it on the right column, the exponent is 1. So if you notice here then, and let's go ahead and let's start out here as we work through this. Okay, you notice then that in the for unimolecular reactions, okay, for unimolecular reactions, okay, and again, make sure you understand, an elementary step is a chemical reaction. It's a reaction in which it's a very simple reaction, which you get reactants go into products. Okay, there are no other steps underneath it. Okay, and so if you take a look at this, then you have a exponent here of 1. Okay, so there it is. So you have that come into product, and if you that's what's defined then as a unimolecular process. Okay, unimolecular reaction. You have one species, okay, one reactant leading to the product. And if you notice here, the exponent for the rate law then is also 1. So for elementary steps then, okay, those steps, the balance equation will give you the exponent for your rate law. Okay. So for the bimolecular reaction here, if you take a look at this one, essentially if you take two these reactants here and they're the same, and you combine them together. So this is a process that we refer to as dimerization. Okay. The balance equation then is going to give you two of the reactants here. And if you notice, the exponent here is also 2. Okay. So with the elementary steps, that is, if you obtain a rate law here, okay, and this is what we'll need to be able to do as we move on with this. So this is what we get. We don't see this part here, folks. Make sure you understand that. We don't see this happening. Okay. But we can obtain this rate law here through experiments. So we can obtain this rate law here. And so if you have a rate law here, and you know that if this is an elementary step, then you know then whatever that reaction is, it's going to be a bimolecular reaction. Okay, so that's what you can do with that one. Okay. Same thing holds true with this reaction. This is also a bimolecular reaction, remember, because the overall order number, okay, overall rate order is going to be the sum of these two individual exponents, and that is a second order reaction as well. And so therefore, it's going to be bimolecular. A termolecular reaction then just simply means then that you have then 3, the order number is going to be 3. So if you notice here, again, the coefficients of the balance equation is 2 and a 1 here. You have 2 and a 1 here as well. So you have then, when we talk about a termolecular reaction, we have then a third, you can see here, it's going to be overall third order rate as well. And when we take a look at the rate law, okay? So what you need to make sure you understand then is that with these elementary steps, and only with the elementary steps, do the coefficients and the exponents for the rate law coincide, that they are exactly the same. Okay? And we're going to use that to our advantage when we start talking about mechanisms a little bit more and how we can prove mechanisms, but make sure you keep that in mind as well. Now, with these reactions here, we typically see then the binary, and we see the unimolecular reactions. Termolecular reactions, they don't happen too often, and we'll talk about why. We'll talk about why towards the end of this chapter. But primarily, you're going to see then unimolecular and bimolecular reactions. Okay? All right. So with that said, then let's talk about these mechanisms a little bit more before we go in general before we go on. Okay. So typically, then not all of the steps, not all the elementary steps in a chemical mechanism, occur at the same rate. They don't. There will be some steps, some elementary steps that occur faster than other elementary steps. There will be some that are, and so because of that, we have what's called then a rate limiting step. Okay. So you can imagine then that the elementary step that is the slowest step, what we refer to as the rate determining step. Okay, this is the rate limiting step. Okay, that will determine how fast the overall reaction will go. Okay, so you can imagine if you can imagine this here, the flow of sand here. Okay, so if you notice then the two openings down here, they're larger openings, and the upper opening here is the smallest one. The rate at which the sand will empty from the top container here and into the bottom one will not be determined by these larger openings. Okay? It's going to be determined by the small opening here. So this small opening here determines how quickly the sand will flow. Okay? And that's going to be the same thing with mechanisms. Whatever the elementary step is going to be the slowest step, that's going to be the rate determining step for the overall reaction. For the overall reaction, it has to be, because it's that particular step that will determine how quickly the reaction will go. Okay, so you can imagine it as kind of being the bottleneck. So as fast as the sand will flow here through that narrow opening, that's as fast as the sand will go from the top down to the bottom. So you can imagine here, the top being the reactant, the bottom being the product of the overall reaction. Each one of these necks here represents an elementary step in our chemical reaction, right? So with that said, then it's going to be this very first step right here that is going to be our rate determining step. So we need to make sure we keep that in mind as well as we progress forward in our discussion of the reaction mechanism. Okay, so reaction mechanisms then will always be defined, or the overall reaction, the speed of the overall reaction will always be defined by the one elementary step, and it's usually only one. There's not multiple rate determining steps. It's only one. So the overall reaction will be determined by the one slow step, the one slowest elementary step, the one slowest reaction. Okay, all right. So that you need to keep in mind as well, because what we can do then is, if we understand that, okay, whoops, sorry. What we can see then is that with this reaction here, okay, the rate then is, this is our rate here. This is the rate law that we're going to use then, okay, and we're going to see then that the first step here is going to be the rate determining step, okay, because the rate here defines the transition from the two nitrogen dioxide molecules to the intermediates here. Okay? And so that's what we want to make sure we keep in mind. And I want to go through this a little bit more with you in just a moment as well. Okay. All right. So let's make sure you understand this. Okay? So this is the chemical reaction that we are given. Okay, this is the chemical reaction that we were given, and these are the two-step. This is a two-step mechanism. Okay, so this is element. You can imagine that the step one. This is elementary step one. This is the first elementary step. And if you notice, and I'm gonna write this in just to make sure you remember what elementary step is. Okay, so this is elementary step number one. This is elementary step number two. So this is a two-step mechanism. Okay, it's a two-step mechanism. And what I'd like to do here then is, let's write out I'm going to write out underneath here the each reaction here. So this is going to be a bimolecular reaction here. So it's going to be NO2 plus NO2 to produce for us then NO3 plus, sorry, let me go into this, NO. Okay. Okay. Down here, then it's going to be NO3. Second elementary step, it's going to be NO3 plus CO to give us NO2 plus CO2. Okay. All right. And here we are given a rate constant for each one of these steps. So technically, we should be able to write down a rate law for each one of these reactions. So remember, an elementary step is a reaction. Okay, and so we should be able to write out the rate law for each one of these. And let's go ahead then. Let's write out the rate law for the first step here. Okay, so this is going to be the rate. It's going to be equal to K1 NO2. And this is a bimolecular reaction, so it's going to be NO2 squared. Now remember, for each elementary step, the coefficient will represent then the exponent for our rate law. Okay, so that's what we have right there. Right. So with this second reaction here, we can write out the rate law then as the rate is going to be equal to, and remember, the nitrogen trioxide here, NO3, is an intermediate, and the intermediates do not appear in the rate law. So that's why we leave that out. Okay. And so with that said, then the rate law then for the second reaction then it's going to be K2, and it's going to be CO. Okay. And the concentration of CO. Okay. So understand what we've done right here is that we have determined the rate law for this proposed step right here. So understand, this elementary step number one is what we are suggesting that's happening. These two steps here is what we are suggesting that's happening as we go for this, from the starting components here to this end. So this is and if you want to think about this, this is the main reaction. This is the reaction that we are studying, and these are the steps that we are saying that occurs when you go from these main reactants to those main products. Okay? All right. So with that said, then we can take each one of these here. Okay? And so we're proposing then that in order for this reaction to go from reactant to product, these steps have to occur. But what we do then is we propose a rate law for each one of these as well. For each step, we propose the rate law. Okay? Now, if you notice then, what I give you here in red, that rate law is what we have experimentally determined. Okay, so you will be typically given this, okay, and the problems that you're going to do, you'll be given this. So this is our experimental rate law. So this is the experimental rate law, meaning then that this is what we actually observe. Okay? This is what we are proposing. These two rate laws here are what we are proposing, okay, is happening. And so the experimental rate law is given to us right there. And so what has to happen then is the rate law that we propose, so the ones down here, have to be supported by this rate law right there. And if you notice, we see that happening in the very first step. Okay? So that the rate law for step number one corresponds directly to the experimental rate law that we have observed. So what does that mean then? That means first and foremost then that, sorry about that, you guys. First and foremost then that that this mechanism could be correct. This mechanism here is possibly correct. Okay? Now, would there be other mechanisms that would propose that could also be correct? Sure. Remember, I told you there's not one mechanism that absolutely shows that that is correct. Okay? These are just steps that we have suggested could be the mechanism for this reaction. However, what has to be true, and we'll talk about this in just a moment, there are two criteria. There's two criteria that have to be met up with each mechanism that's proposed in order for those mechanisms to be valid. Okay? The first one then is that the rate law that we come up with for the steps, okay, has to correspond to the experimental rate law, what we observe. Okay? Secondly, each individual step, when you combine them together, should reduce down to give you the main reaction here. It should give you that. And if it doesn't, if either one of those criteria are not met up with, then the mechanism is wrong. And so that's the challenge with doing these mechanisms, folks. We're doing easy reactions here. You can imagine trying to get those two criteria met up with for more complex chemical reactions. And that's why mechanisms, I think those folks who work in that field and are coming up with mechanisms or as they work, they're trying to come up with mechanisms for a reaction. It takes a really bright person who can organize a lot of different thought processes in order to get that done. Okay? So with that said, then, if you notice here right now, then the mechanism here seems to be valid so far because the first criteria is met up with. The rate law that we proposed right here, and the red box in the middle, corresponds to the rate law that we observe, the experimental rate law, which is the red box on the top. Okay? So criteria number one has already been met. Okay? And so the second criteria then would require then that the two mechanisms down here, so let's go ahead, the two elementary steps, when you combine them together, and I'm just going to go ahead and draw a line right here. Okay? And so when I say combine them together, that means that basically we're going to add them together. Very much like you remember with Hess's law, we add them together and we see then that the nitrogen trioxide, that cancels out. Okay, so that is gone on both sides here. Okay, and so one nitrogen dioxide here and one here cancels out because they are on opposite sides of the arrow. And look at what we're left with here. We're left with then nitrogen dioxide on the left plus carbon monoxide on the right, and we're left with nitrogen monoxide on the right, and carbon dioxide, which corresponds directly to that main reaction. So the second criteria has been met. Okay? And so with that said, then that's what we'll be practicing in today as we go through this. Okay. All right. Last thing I want to point out to you then is it looks like then the rate law here corresponds to the first step. Okay. And so therefore that means then this first step then is going to be our slow step. So elementary step number one, this is going to be our slow step. Remember, because you said then that the slow step, the rate for the slow step determines the rate for the reaction as a whole. So that's why this right here is the rate law for the overall reaction, the main reaction, because this rate law then corresponds to the very first step here. And so therefore, that's how we can also conclude that this first elementary step is also the slow step. That's the rate limiting step. So the rate determining step, rate limiting step. I learned it as rate limiting step, but you'll also see it then as the rate determining step, RDS as well. Okay. I'll be referring to it rate limiting because that's how I learned it. Okay. All right, very good. Let's go ahead then and let's quickly review what I have here for you. Okay. All right. All right. I'm sorry, we got that. Okay. We'll talk about this in just a moment. Okay, but let's go ahead then. And so that's what I told you with the for the mechanism then, for the mechanism to be valid, two requirements must be met. Okay? And that is, and like I pointed out to you just now, what has to happen then is that the experimentally determined rate law, okay, it has to match whatever rate law we are able to propose for our mechanisms. And then finally, the sum of the elementary steps, when you add them together, must be the same as the balance equation for the overall or our main reaction. Okay, our main reaction. And so with that said, then, even after these two criteria, the test of validity, and so I refer to this as a validity check, and I'll be referring to it as that as well. So even so, after our validity check, that means that we have checked to see then that our mechanism is valid. Even after the validity check, that does not mean that our particular proposed mechanism is correct. Okay? Someone else can propose a different mechanism that also meets this criteria, these two criteria here, and that particular mechanism will also be as valid. Okay, so for right now, it seems like the check for validity seems to be pretty flexible, seems to be pretty wide open. But as we go on, you can see then that it's not that easy to get both the sum of the elementary steps and our rate laws to match up with the experimentally determined rate law. Okay, so that's not as easy as it looks here. Okay, and so I think working this out, you can see then the changes. I'm sorry, you can see then how difficult it is in order to get these two steps met up with. Okay, all right. So with that said, then what I'd like to do then is let's go ahead and I want to look at a problem. I want to do a problem with you, and just to show you how we get this done. Okay. All right. Let's go ahead then, and I'm going to go ahead and let's take go grab your book, go pause the video, grab your book really quickly, and what I'd like to do then is let me go ahead and do this out and open up a whiteboard here. I want to go ahead and do number 61 with you in your book. So this will be part of your homework for tonight. So I'd like you to work on the mechanisms here. Okay. So let's go ahead and let's take a look at 61 here, and let me show you here. Okay. So number 61. I'm sorry. Yeah. There it is. Let's go ahead and let's take a look at number 61 in your book. And this is on page, well, I forget what page. Let me get it straight real quickly. So let me go ahead and open this up. Share this with you. Okay, there it is. Okay, so let's go ahead and let's take a look at 61, which is on page 597. Okay. All right, so let's do number 61 from your book on page 597. Okay. All right. So let's take a look at that problem. So they give you a proposed mechanism, and let's go ahead and let's write this out. So they're saying then that, so we don't know what the overall reaction is. So in this problem right now, they're asking us to find the overall reaction or the main reaction. Okay, so the overall reaction. Okay, and so we don't know what that is. Okay, so we're going to find that. Okay, and then they also want us to find then the rate law for this as well. Okay, so the overall reaction and the rate law that we expect for this overall reaction. Okay, all right. So what they do then is, so we're kind of working backwards here a little bit. Okay, so that's fine. So they give us then the steps, the elementary steps. Okay, so step number one, elementary step number one, the first reaction that has to take place then is going to be then C4H9Br. Okay, that's going to break down. So this is elementary step number one now. Okay, to C4H9 plus Br minus. Okay, elementary step number two. Okay, this is reaction number two. We take C4H9 plus, and it combines with water. Okay, to form then this complex here, C4H9 HOH2 plus. Okay, and then step number three, the third elementary step, then we get the C4H9OH2 plus, combine it with another water to get us then C4H9OH plus hydronium H3, oops, sorry, H3O plus. Okay. All right, so let's go ahead and let's go and do, I'm sorry, and then they tell us one last thing here. They tell us that the first step is the slow step. Okay, the second and the third elementary step are fast. Okay, all right, so let's go ahead then and let's do a couple things before we work out this one. So they want us to find the overall reaction, and then they want us to determine the rate law for this particular reaction here. So let's go and do this first. Okay. First of all, hopefully you recognize that the first elementary step here is going to be a unimolecular. So this is a unimolecular process. Let's go ahead and write that in. Why is it unimolecular? This elementary step here has only one reactant to start out with, only has one species. We see then that the for the next elementary step, this is going to be a bimolecular reaction. And then same thing holds true for the second one. It's going to be bimolecular as well. And so why are both of these bimolecular reactions? You have two reactants involved in this. Okay, so this is going to be then what we can use then to determine the rate laws for each one of these. And we'll do that in just a moment. Okay. All right. So let's go ahead then and let's obtain the overall rate law first. The overall rate law, I'm sorry, the overall reaction then is going to be basically taking every one of these elementary steps here and then combining them together. How do we combine them together? Basically, then we're going to determine then whichever species is the same on both sides of the arrow, they cancel out. Okay, so if you take a look at this here, we have this particular compound right here. Let's go and take a look at this. This compound here appears on the right-hand side, and then occurs again on the left-hand side in the second elementary step. Okay, so this is what we refer to as an intermediate because it's produced in one step, okay, and then it's used up in the next step. Okay, so this is an intermediate right here, but because it appears in one step on one side of the arrow on one step, and on another side of the arrow on the second step, it basically cancels out. Okay, so it will not appear in the final reaction. Intermediates do not appear in the overall reaction because they get produced in one elementary step and then they get used right again in the next step. Okay, and so if you notice, then we have another intermediate right here. We have this intermediate right here that is produced in the second step. Okay, so it's produced in the second step here, and then it gets consumed in the third elementary step right here. So we have a second intermediate here as well. So we have two intermediates that are formed in this reaction. But as such, again, they do not appear in the overall final reaction. Okay. All right. So with that said, then, if you notice, then nothing else can cancel out like we did with these intermediates. Now, understand, intermediates are not the only species. that will be canceled out. Okay, but what you want to make sure you understand is that intermediates will not appear in the overall reaction, and they won't appear in the rate law either, because again, they do not. I'm sorry, they won't appear in the overall rate law because they don't appear in the overall reaction. Okay, so let me go ahead and actually let me specify this. Let me go back up here. So this rate law here is what we would expect. So this is our what we should have observed if our mechanism is correct. So let me specify that. Okay, so therefore intermediates will not appear in this observed rate law either, because they are not going to be a part of the overall reaction. Okay, they are species that we propose should form in order for the reaction to occur. Okay. All right, so with that said then, let's go ahead and write down what is left over. On the left-hand side of the arrow, on the left-hand side of the arrow, then we have C4H9Br. We have two waters, two H2Os. So we have one water here, okay, and another water here. So that's two H2Os. On the right-hand side, then we will have C4H9OH plus Br minus plus H3O plus. Okay. And that, folks, will be our overall reaction. And we will go ahead and write that in. Okay. That's as simple as it gets, folks. Okay. So our overall reaction then, our first answer, we got our first answer then is going to be C4H9Br. Okay. And we'll go ahead and write it up here, plus 2H2O. And that's going to give us C4H9OH plus Br minus plus H3O plus. And the reaction, folks, should, this overall reaction, based on what we have here, should be balanced and correct. The stoichiometry should be exactly the way that we expect it to be. Okay, so there it is. That is the overall reaction that we have here. Okay. Now the question is, how do we obtain the rate law? Okay, so the rate law for this reaction. Well, the rate law for this reaction has to be taken from one of the rate laws here, rate laws for one of these elementary steps here. So let's go ahead and let's write out the rate laws for each elementary step. Okay, let's write out that rate law for each elementary step. This is a unimolecular reaction. So therefore, and let's assign then, I'm sorry, one last thing. Let's assign then a rate constant for this one. We'll call that K1. That's going to be K2, and that's going to be K3. Okay. All right, so the rate law then for the first one, for elementary step number one, then it's going to be the rate's going to be equal to K1 times the concentration of C4H9Br raised to the first power, because this is a unimolecular reaction. Okay, the rate law for the second one. So this is rate law number one. Rate law for the elementary step number two should be then K2 times the concentration of C4H9 plus times the concentration of water, and this should have 2 with the balance equation here because this is a bimolecular reaction. Okay, and then finally the rate law for the third step then is going to be rate for 3. It's going to be equal to then K3 times C4H9OH plus times the concentration of water. So again, bimolecular, so we expect two species here as well. Okay. All right. So if you understood what we just said here, then rate law number 2 and rate law number 3 cannot be the overall rate law for this reaction. Why? Because in both of these here, we have the intermediate present. Here we have C4H9 plus, and we said that's an intermediate. That disappears. That goes away in the main reaction. Okay. And same thing down here. We have C4H9OH, which was also an intermediate, which leaves us then this one rate law here as being the only one left, okay, which is the very first one right here. Okay. And so that is then going to be the rate law, the overall rate law for this reaction. Okay, so that's going to be the rate. I'm sorry, this here. Okay, that's going to be then the rate. It's going to be equal to K. So we'll just call this K now. It's just a constant, okay, times the concentration of C4H9Br. And if you notice then, the rate law here does not include water. So the rate law here does not include water, even though water is in the main reaction here. Even though water is in the overall reaction in our rate law here, it does not include water. And so if we actually observe the rate law here, okay, if we observe that, if this is what we observed, so let me go ahead and try to finish up here. Sorry, if this is what we observe, water then is not going to determine the concentration, the speed, the kinetics of this particular reaction. It's only going to be then the C4H9Br here that's going to determine that. Okay, so the bromobutane here is what's going to determine how quickly this reaction runs. Okay, all right. So with that said, then it also makes sense in the context of the rate limiting step here, because if you notice, the step number 1 is going to be the rate limiting step. It's going to be our rate limiting step because it is the slow one right here, and we expect then that it's going to be that rate law that determines then how quickly this reaction runs, and we have confirmation of that right here. Okay. And so that is the rate law. That's the overall reaction for this particular process. What I would like to do tomorrow then is that what we're going to do is we're going to start out with the overall reaction, and then what we're going to do is we're going to determine a mechanism. We're going to try to determine a mechanism for the reaction, and then also confirm that with the appropriate rate law for each elementary step. And so that's what I'd like to do tomorrow. Okay, so what I'll do is I'll hold off on the homework for mechanisms, and I'll have you do that over the weekend. And so we'll do that tomorrow. On Friday then, hopefully. So there will be we don't meet on Friday, but I'll have a lesson for you, okay, posted. And so with that said, then we'll try to finish up with this chapter by tomorrow. Hopefully, wrap things up on Friday, and then start chapter 17 on Friday as well. Okay. If there's any changes, I'll let you know about it. But that's what we should expect. Okay. All right. But if you're interested, go ahead and take a look at set B from chapter 12 and start working on these mechanisms and see if you can work through some of these problems. And like I said, I'll work through more of these for you tomorrow. Okay. All right, folks. Have a good rest of your day, and I will see you tomorrow. Okay, bye.